because the FDR didn't have that the wall, the switching terms came into place after FDR. It's not like you broke the law, so that will all in place.
Well, you will abandon all laws.
I don't know. He's close enough to getting his leash as this. He starts to make before he's really done. Yeah. And his son and old class will really be helpful too, right? Who the heck names their son that? That's so happy.
I'm sure
Ready? Okay.
Hey, good evening, everyone. So this stuff's pretty cool today. We're doing 13.1 and 13.2. These are on vector functions. And then we'll do derivatives and integrals of vector functions. We've already written a line as a vector function, right? But that's what we're doing, but these will be different from lines. We may get a line in there, but we're going to have vector curves. So you can also call these vector curves. You can call them space curves if you want. Sometimes they're in two-dimensional space, but we're going to look at a lot of problems that are in three-dimensional space. Might even look at it with the software. We can draw them on our papers. I'll draw it on the board, but sometimes it's neat just to see it done with, something like I'll use wind plot. We'll make these graphs. So I'm going to start with a two-dimensional vector function. And I'm just going to call it r of t. And I'm going to set it equal to, let's see, 4 square root of t and 4 minus t for the x and y components. And we're just going to go ahead and sketch this. We'll sketch this vector curve. So we'll talk about, well, how do you do that? Because of the parameter involved. This is the x-axis. That's the y-axis, and you have these t's in here. T is that parameter. And so it's the idea we got a parameter, and we got our x and y variables. So how do we sketch a vector curve? One way is just to make a table. Just make a table. You got t's, you got x's, and you got y's, and you can simply make up t values and plug them in. Where's the x and the y? Right here, that's the x, and that's the what? The y. So just remember that. There's x, there's y, so when it comes down, where do I start? I don't know where to start in terms of making this sketch. I have to sketch this in the xy plane. You can simply just make a table, and you get to create t values. So how about we'll sketch this from t equals 0 to t equals 4. All right, 0, 1, 2, 3, 4. Now we plug these in. What's 4 times square root of 0? 0. 4 times square root of 1? 4. 4 times the square root of 2 is 4 root 2. We can look at that value. 4 times 1.4. 3. 4 times root 3. At least this is neat. What do you get there?
8.
8. What are these? Well, 4 minus 0 is 4, 3, 2, 1, and 0. And then you'll notice, oh, I've got a curve. And I can just go ahead and plot these points. We'll definitely plot this one. This one's nice. And we'll definitely plot this one. This one's nice. And we'll plot this one too. All right. So I'm going to go out to, it looks like I have to get at least out to x equals 8. 1, 2, 3, 4, 5, 6, 7, 8. And for y, I only have to get up to what? 1, 2, 3, 4. 4, 8. Let me plot these. It was 0, 4. Then it was 4, 3. Then it was 8, 0. You can plot these if you want as well. But you'll notice it's curving, right? It's not a straight line. If you wonder what a straight line would have been, this would only have like 4t. No t squares, no radical t's, you get straight lines. I'll connect this curve. Now what you should do with vector curves, is put an arrow to indicate the path. The path in which t is increasing. Just put it anywhere on the curve. So which way is this thing going? That way or this way? anywhere you want, you can just go, all right, it's going that way. That gives the direction as t increases. Of course, we can apply to more points. And you got the vector curve. There is another way to do this. This is a simple way. This works all the time, especially when it's in two-dimensional space. But there is another way where you can actually eliminate t, eliminate the parameter, and then you just have x and y, and you can make the curve, right? You'll have a curve in terms of x and y, and you sketch it like you're in a, back in a pre-calculus course. So just another way. You can't do this with all the problems, but many you can. You look at something like this, you're like, well, can I just eliminate the parameter? And you'd have to do this by substitution. So x equals 4 square root of t. Y equals what? 4 minus t. So is there a way I can substitute this into there and just get x's and y's?
Yes.
What would t equal to here?
X over 16. X squared over 16.
You could do that, or even in this case, if t would equal what?
Oh, 4 minus 1.
Y plus 4? And where can I substitute this? Right into there?
Mm-hmm.
And this is one way, and you got x equal to what? 4 square root of y plus 4, right?
Uh-huh.
Awesome. So I mean, it's just, but there's one way you can do is look at, hey, I got a curve now.
Wouldn't it be 4 minus?
In this case, so this would be, if I did the t, let's see, t would equal, yeah, 4, would it be 4 minus y?
Yeah.
Yeah, thank you so much. So in this case, let me rewrite that. Thank you so much. T would equal, we add t to both sides, 4 minus y, and then we would have x equal to 4 times the square root of 4 minus y. But who knows, maybe that's not so helpful to you when it comes to sketching the curve, right? You could square both sides. What would you get?
X squared.
X squared equals 16. Now you just have what?
4 minus y.
You're like, oh, okay, I see. Sounds like this is part of a parabola. What would that be? 64 minus 16y. You have that relationship. So I just wanted to point that out. Sometimes you might find that easier just to eliminate the parameter. Cool. Now, these all vector curves. Can we draw some certain vectors on this thing? I'm going to start with the position vector. Can you draw the position vector at t equal to 1? Can we draw on this sketch the position vector at t equal to 1? The position vector will always start from the origin, all right? And that tip of that vector will land right on the curve. So when we're looking for r of 1, and what do you plug in here? That means you just go to the original function, you plug in a what?
1.
A 1. What would you get? Want to be these numbers?
4, 3, yeah.
4, 3. And I'm going to sketch that. Means I went over 4 and 3 what? Up, but this is the position vector, so I'm going to label this. There it is, give it an arrow. That's r of 1, I'll put an arrow on there. See how it's tip laying right on that curve? Cool. Now, it's okay to talk about it right now because we're covering both sections today. We're going to be doing derivatives. So, can we look at the derivative of that r of t, which would be r prime of t? Let's check that out. Let's look at the derivative of r of t. Well, the derivative of r of t would be what? R prime of t. If that's the position vector, what do you think r prime of t would be? There's a position, starts with a v.
Velocity.
Velocity. You can call this the velocity vector. For right now, I'll just leave it r prime of t as the derivative, but it's also called a tangent vector. So r prime of t is, you can think of it as the velocity vector, but also as the tangent vector. So when I say tangent, you know about tangent lines? You bet that vector will be tangent to this curve. Okay? So let's find r prime of t, and then we'll find r prime of 1. We'll find the tangent vector equal to 1. All right. How do I do these derivatives? So really, this comes into play in 13.2, but it's okay to talk about right now because we're doing vector functions. R prime of t be the tangent vector. Let's see what we get. All right, let's derive or squared of t. That's t to the 1/2. So 1/2 times 4 is
2.
2. Then you decrease this by 1. 2 over square root of t?
Mm-hmm.
Nice. That's an easy derivative. What's that?
-1.
All right. So now after this, right underneath it, can you find the tangent vector at the value 1? So this is going to be at t equal to 1. Find the tangent vector at t equal to 1. So that'd be r prime of 1, substitute a 1, what do you get? 2 comma what?
-1.
Negative 1. And again, these are derivatives, so this is something that actually come into play in our textbook in 13.2. These sections go together. So if we did a vector function, we can just draw some tangent vector. When I draw this, I need you to start this from the tip of your position vector. And when you draw it and sketch this vector, you'll notice it'll be tangent. So I gotta go what? 2 to the right and then 1 down. True? But I'm not drawing it from here, I'm just gonna draw it right from here. So I go 2 to the right, and I go down, run, and does that look like it's tangent?
Mm-hmm.
You bet. And I'm gonna label this r prime of 1. You can also call it b of what? 1. It's the velocity vector. So another thing, you can call this the velocity vector. I'll put a v on there if you want. Velocity.
So the tangent vector is called velocity vector.
The velocity vector. If we're thinking of this in terms of the position of some object, right?
Okay.
And it's moving, or a particle,
Uh-huh.
or it's a bug, some bug flying, right? The velocity vector is the tangent vector. Well then, what would r double prime be if this was position?
Distance, right?
The derivative position, we got velocity. The derivative velocity is
Acceleration.
acceleration. So let's find the acceleration vector, which would be r double prime of t, right? Okay. Well, I've got that up here. Can I erase these points? Okay. Still right here. So now we're going to have to take the derivative of that. What's a prime of t? Which would be r double prime of t, right? We put 2 slashes on there. Let's see what we get. Are you ready? See, when that's 2t to the negative 1/2. You got to take a 2t to the negative 1/2 and apply the power rule. So what's negative 1/2 times 2? Negative 1. T to the negative 3/2. Okay. And what's the other component? What's the derivative of negative 1? 0. So when I just took the derivative of this, and we got the negative 1t to negative 3/2, I took the derivative of negative 1, constant 0. Can we write this again then? A of t, or r double prime of t, is negative 1 over a what? Q 3 0. Now, can you find the acceleration vector at t equal to 1? This will be at t equal to 1. Can you find the acceleration vector?
-1.
Negative 1 and 0. Acceleration vectors are funny. Sometimes they're like this, sometimes they're like this. If it's a circle, if you get a particle that's moving in a circle, which way is the acceleration vector? Point. Anybody know? It points inward. Very good. He knew. You can actually, if we took a vector function with a circle, you'd notice that. Where's this thing? See, it's funny. What is this? This isn't much, is it? It's gonna be a little beep. So we got to move. And we also draw this from the tip, from the same point you're drawing the tangent vector. So I'm going to go what? 1 in that direction, but I won't go up. Hold on. So just from this point, just go a little bit, stop. And that's your acceleration vector. A of 1. That little guy. Good job. Hey, any questions on that? Cool, wait, you bet. So what if something going like this? You'll notice like that acceleration would be like this. The tangent vector would be like this. And these two vectors would be perpendicular to each other. Cool. Alright, let's look at some vector curves that are in three-dimensional space. So I'm going to start out with this guy. R of t. I mean, when they have, I'm going to write this, but we won't sketch this. They have vector curves like this in there. And absolutely, you can sketch that, but what could you do? You could just make a what? You can make a table and just start what? Plotting points, right? So we won't sketch this. I just want to give you an example. You'll see some problems in section 13.1. They'll say, sketch the vector curve. It's in three-dimensional space. You're like, well, where do I start? You just end up what? You make some t-values. You get a sense of how this thing's going. Okay? What we're going to look at is problems where maybe we don't have to sketch so many points. So other than this, here's the one we're going to do. How about this is sine of t. This is cosine of t. And this is t. And this is the x component, and this is the y component, and this is the z component. Surely I can do what? Surely I can make a table and make up some t-values like what? 0, pi over 2, pi, 3 pi over 2. But we'd still get these little points over the place. It wouldn't help us much in terms of making a really decent sketch. So, let's at least get 1 point just to get it started. What's going on at t equals 0? Sine of 0 is 0, cosine of 0 is 1. And then this t value would be what? 0. All right, so there's 1 point on the curve. There's 1 point on the space curve. But I want you to look at something else. Let's look at relationships. So I'm going to hide this.